Okay, welcome back. We're going to go through part two now, and we're going to talk a little bit about pneumatic flow, or how fast does something move in a pneumatic system. So when we talk about pneumatic flow, a couple things to consider here. The flow, or the rate of air movement, depends on a few different terms here. Now, I'm going to put the caveat in here that I'm assuming this is adiabatic. It is not. Adiabatic just means there's no heat transfer in the system. There's actually a little heat transfer. You can see that because the compressor gets hot when you use it, and then when the air expands, it gets cool. But for this discussion and for our level of engineering in it, we don't need to consider that very much. So we're just going to look at the flow depending pretty much on the pressure differential between the input and the output side of the actuator, the fluid density, and then any restrictions in the line. Now, when we talk about flow, a simplest way for us to think about it is what's called a C sub V, or coefficient of flow. And what this does is it's a number that represents resistance to flow or restriction to flow. A larger number means there's less of a restriction of flow, essentially. So when we look at pneumatic flow and we plug it into the pneumatic equations, which I won't get into too in depth here, they're basically some integrals. It's calculus based. But when I look at pneumatic flow, I consider that as a Q, or a flow rate. And with a fixed orifice, like a solenoid valve that's of limited size, the C sub V happens to be, for those little solenoids I showed you, 0.24, and using air that's about at room temperature. What I see here is the volume in cubic feet per hour is inversely proportional to the differential in pressure. And what I mean by that is if there's no back pressure on the other side of the piston, or on the other side of the solenoid valve, is another way to think of it, my flow is really high. You can see that at 60 pounds per square inch of differential, meaning that there's no restriction on the other side of the piston, I have a pretty high flow rate here, 1.9 or so, it looks like, cubic feet per hour. So a pretty decent flow rate. Now, as my pressure builds up on the other side of the piston, the flow effectively drops off. And notice this, when I get really close to having a pressure, back pressure, close to the system pressure, my flow rate goes to zero, really, really steep. So it trails off, and it's really a function of the square root of that pressure differential, or delta P. So why do we care about that? The reason is the load impacts the speed. So as the load I put on a pneumatic actuator approaches the maximum force available, the piston slows way down. Now I think of load as a force of resistance. The load pressure, or the equivalent of back pressure there, is that force divided by the area. Once the force that the piston can generate is opposed by a resistance force equal, then I have got no differential pressure. I effectively have no flow. The extension won't happen on the piston. So that's our first takeaway. If I increase the load, the piston goes slower. The second takeaway here is this is how I make a piston go slower. I restrict the outflow out of the opposite side where it's moving. So if I'm trying to extend it, all that I do is I slow down the outflow of air from the load side. And I do that using a little pressure regulator. They could be inline, they could be fitted to the exhaust valve. It doesn't really matter where you put them. What this does is restricts the flow of pressure, or the flow of air coming out of the piston as it moves opposite to its extension. You can put these on both sides. They only restrict flow in one direction though. So restricting my outflow also adds to the load pressure and slows the piston down. And we'll look at that in our lab. So let's go back to our basic idea of force. The force that the piston generates is the pressure of the system times the area of the piston. So I look at this and I say, hey, if I want to get more force, given a fixed pressure, I need to increase the piston size. That's it. Now, I can't necessarily increase my flow rate when I increase that piston size. So if I have a flow that actuates the smallest piston in about 0.2 seconds, but I just make the piston bigger, I get a chart that looks like this. And what this is saying is if I used a 1/2-inch piston, if you could find one of that size, these are just nominal mathematical sizes, not actual sizes. But if I used a 1/2-inch piston here, it would generate about 11 pounds of force. The volume here is about 0.785 cubic inches. And I said it would take 0.2 seconds to fill. I don't know if that's real or not. I'm just saying that as a comparison. It's moving at 40 inches a second. That's pretty zippy. Pretty zippy. Now, as I move up in size on the piston diameter to 1 inch, I've doubled the diameter, but notice I've cut the speed by a factor of 4. So my speed of motion is inversely proportional to the square of the change in diameter. And all that that's saying is it takes way more volume of air to fill the piston as it gets bigger. Now, a lot of times in FRC, you'll see somebody use a giant piston, like a 2-inch piston, and 24 inches long. Here's the problem with using those massive air systems without a massive supply system. It takes a long time to fill that thing, 20 seconds almost. It is not going very fast. And it took a ton, 96 times the air volume as it took to move this little 1/2-inch piston. So the volume required to move the piston is substantial. So for that reason, pneumatics are not really suitable to generate massive amounts of force in an FRC robot. They just aren't. The most typical piston you're going to see is down here at 3/4 of an inch or smaller. Because if you need more force than that, you need to think of a different mechanism. But it's really useful for really quick, short activations. So let's look at some of those. So if I had a 3/4 inch piston at 60 psi with a 1/4 inch rod shaft, now that's pretty close to what they are. The question is, how hard will it push? So the way to compute that is to calculate the area of the piston and then multiply times 60 psi. To find out how hard it will pull, calculate the cross-sectional area of the rod and subtract it from the area of the piston. Then multiply that times 60. The volume of the air consumed is the volume of the piston, which is the area of the piston times its stroke length. Now it's going to be a little less on the retract than it was on the extension, and we saw that already. But the next question here is, what is the stored energy in the air? So if I've got a tank, and those tanks are about 35 cubic inches at 120 psi, the amount of energy I store based upon an adiabatic system is about 35 cubic inches times 120 pounds per square inch. Or I'm going to get 2,100 pound inches of work that can be done. That's potential energy. So if I say to move a 4-inch piston once takes that volume of air of 106.2 pound inches to move it once, and I've got a volume of air in the storage tank of 4,200 pound inches, I can move that piston now about 39 times. Now, is that perfectly true? No, it isn't. It's a simplified calculation for you. because the reality is as I drop down below 60 pounds per square inch of pressure, it drops off, the movement drops off, and it may not move. That's a simplified idea, though. So we can estimate about how many strokes the piston can make. So our next exercise is going to be an exercise in doing some of these calculations. We're going to do this in class together. So if you go to your next module, you'll find the companion to this, 2.1b, which is the pneumatic calculations. Let's do a quick recap on what we've learned about pneumatics. The first one is that force is always a function of pressure times the area. If I want more force, I either need more pressure or more area. The second one is cylinders always push harder than they pull because the rod displaces area on the piston where the pressure can be applied. The third takeaway is that the flow rate determines how fast the piston moves. That flow rate is driven by the pressure differential. So is the piston loaded or not? Does it have a flow restrictor in it or not? And then the resistance to flow. How big is the valve? Bigger valves allow more flow, allow faster movement. A big cylinder pushes hard, but it goes slower. There's no free lunch here. The amount of power I can provide, or the rate of doing work, is really related to the flow rate. And the last one is very large loads are probably not suitable for air power. There's just not enough onboard compressing, storage, or size in the lines to make a massive amount of force using pneumatics. So think of a different mechanism. If you're looking to generate a lot of linear force in a rapid time, air is probably not it. All right, we'll move on to our next module, 2.1b, which is working the problems. Thanks for watching.